Long. So many great people. Thank you for coming. This means a lot to me. It means a lot to Brandon. It means a lot to everything. It's fantastic. Something different about tonight, what's fantastic, is we are collaborating with Ya Ya Brewing Company out of the Valley. Has anybody been to Ya Ya before? Yeah? Just one? Got a couple? Okay. Well, I know you have. You fucking own it. Okay. Great, great. So they brought some kegs tonight, and we have basically a tap takeover. And if you have any questions, Jason or myself, you can come and ask. And if you ask me, I'm probably just going to point you in his direction because I don't know much about his beer. But I know it's great. I am drinking the, what am I drinking? I'm drinking the Way Back Home, which is a hazy pale. If you're into hazies, you know, fantastic, go for it. Rock on. Drink beer, talk about stars. It's going to be great. Drink beer, talk about stars. All right, cool. So tonight, the subject of tonight, we're talking about nebula. What is the plural of nebula? Does anybody know? Nebulae. Good job. You're my favorite customer. Okay. Nebulae is the plural. So when we talk about everything as a whole, it's nebulae. That's great. So I picked this background here. You may have seen it on Instagram or Facebook, wherever you saw the advertisement, but I picked this background on purpose. This is my personal favorite. This is the Carina Nebula. This is, if you talk to an astronomer, they're going to call this the Wide Field Carina Nebula. So there's a lot of smaller targets in there, but this is the ultra wide field. The resolution on this shot is so high, you can blow this up to be 8 feet tall and 16 feet wide, and it will be tack sharp. The file of this is like 2 gigabytes. It's unbelievable how sharp that is. So I'm gonna freestyle it. I don't like to have a lot of notes because it's a lot more fun to not know what I'm doing. I'm a lot better at not knowing what I'm doing. So the first question that anybody asks, like people have seen these shots before, right? From telescopes. We have ground-based telescopes. We have space-based telescopes. And they, you know, once Hubble got shot up, you know, back what was it, late '90s or so, or was it the early '90s? When Hubble got shot up into space. Side fact: Hubble was not the first Hubble in space. If you know the space shuttle, the cargo bay of the space shuttle was designed specifically to hold a telescope from inception of the design of the space shuttle. It was supposed to hold a telescope the size of a school bus, precisely, which is exactly how big the Hubble Space Telescope is. It's the size of a standard school bus. It is not the first one that got sent up there. However, it is the first one that is pointing the other direction. So, if anybody knows, the space shuttle was actually supposed to fill a military role, and it was a military project. It went up there to basically place a bunch of spy satellites, more than anything, which is what Hubble was. That's why back in the '90s we could read the date on a dime from space. It's because we had a bunch of Hubble Space Telescopes, and we obviously know the power of the Hubble Space Telescope. This is 6,500 light years away. The light that we got from that shot took 6,500 plus or minus, because things are different distances, to get here and resolve that for us. But one of the big questions about nebulae, we've all seen the fantastic, spectacular images. Back in the '90s, I actually remember waking up before school and seeing the first shots of the Pillars of Creation shot from Hubble, and it blew my mind as a young kid. But the first thing we think about is, are those colors real? When I look up at night, I don't see that. I mean, I don't know about you, but I see mostly dark stuff. It doesn't look quite like that. Those colors actually do exist. This one's probably not the best example of the accurate colors, to be honest. The European Space Observatory, the very large telescope, actually took another shot of this, and it's actually a lot redder than it is orange. This is actually using what's called the Hubble palette. When Hubble actually takes pictures, it doesn't take pictures in color, it actually takes pictures in black and white. But they have these filters that actually spin into the front of the lens, and it can isolate specific types of light, and they'll expose for a certain amount of time for a certain type of light, and then they put all of that data into a folder and know that, okay, so all of those shots were only looking for, you know, where we would see red, or where we would see green, like in other elements. And we'll go into that a little bit later. But the colors themselves actually do exist. I think the best example is actually in my next slide, which is one of our favorites, everybody's favorites. Who knows what that is? It's a constellation, and it's right over there right now.
Orion?
Yes, Orion. Good job, Zach. That is the constellation Orion. Everybody see the belt? The 3 stars in the middle? That is Orion's belt. Extra credit, that's called an asterism. It's like something, it's not a full constellation, it's a piece of a constellation. We call those asterisms. This is one of everybody's favorite, if not mine, for a constellation shot. So this was actually taken by a friend of mine, Rogelio Bernal-Andreo. You can actually see his name up in the top left. He has been noted more times by NASA for an amateur astronomer, or amateur astrophotographer. He's actually been awarded more than 100 times from NASA for his astronomy pictures. Just from those alone, you can call him the best astrophotographer in the world. And you know, having spent as much time as I have with him, he is pretty amazing. This shot is 200 hours worth of data collection. He spent 200 hours with 2 telescopes, gathering all the data to get this shot. And that actually goes into my next point when it came to colors. Okay, so when you look up at the night sky and you look at Orion, Orion is right over there right now. We can go outside right now and look at Orion. It's really easy to spot. But you don't see that big, like, see that half circle there? It's called Barnard's Loop. That's huge. That's like 10 full moons in the sky from one end to the other. It's huge, okay? But when I go outside, I don't see those colors. A lot of that has to do with the fact that our eyes are so small and we can't see a lot of light. That's why we need really big telescopes to gather a lot of light. When you can gather more information over a certain amount of time, you can resolve colors like that. I used to have a very large telescope that I used to use for tours and things like that. And when you looked at the Orion Nebula, which actually, if you see the 3 stars of the belt there, if you go to the right, directly to the right of the middle star there, that really bright region with the purple, looks kind of like an eagle, that is the Orion Nebula, that is the sword. If you look at that with a really big telescope, like an amateur-sized telescope, larger than 10 inches, you know, 11, 12, 15-inch, 16-inch telescope, you can actually start to see color. The aperture of the telescope will actually resolve some color, but still our eyes are so weak that we don't really resolve the color through telescopes that much. If you're in the eyepiece of like a giant telescope that's feet in diameter, then yeah, you can probably get some great shots there. So the next question is, did it lose energy as we get farther and farther away from it? There's a little bit of that, but honestly, if you actually flew up to where it was, this is a good question. It's like, if I flew over there, would I start to see the color all of a sudden? And the answer is, yeah, kinda. But here's my next one. Who here has seen the Northern Lights? Yeah? A few people? Awesome. Great. How many of you have seen pictures of the Northern Lights? Cool. So who raised their hands both times? Gotcha. Okay. So is a picture of the Northern Lights the same as you observing them? No. What's different? The vibrance, the luminosity, how bright it is. So the same thing would actually be apparent if you actually flew out and saw these. The colors would be there, but much in the same way as you would observe the Northern Lights, say. You go there, and you should, by the way, if you haven't before. And I always say that it's not the colors that get to you, it's how they move. That's what really gets to you. It's crazy. And some people say they can hear them, but they're full of shit. Don't listen to them. Okay. But it'd be much the same way. It'd be very faint. Those colors would be there, but they would be faint. Very, very faint. All right? Cool. So nebula. What does nebula even mean? Nebula is actually a Latin word. Does anybody know? You're not allowed to answer, by the way. Who's okay, cool. Brandon's not allowed to answer. Who said it and who got it right? Yeah? You? Yeah. Eric. Okay, cool. It means cloud. It's great. You know why they're called clouds? Nebula? Because before we had giant telescopes, we had small telescopes. When you look at these things in the sky, they look like clouds at night. They look like fuzzy, white, gray patches. Sometimes you can see a little bit of green, sometimes you can see some lavender-ish colors if you have a really big telescope, but they look gray and wispy. The Andromeda Galaxy, this thing right here, before Edwin Hubble, it wasn't called the Andromeda Galaxy, it was called the Andromeda Nebula, okay? Until he saw a particular type of star and realized that it was outside of our galaxy, which is, if you were here 2 times ago, that was a great thing. What's up?
Are you saying that picture, one quick question on the picture, no filters on that at all?
It's hard to answer that directly. So yes, there are filters.
You were implying that if the closer you get, that's closer to what you would see.
Yeah, okay, so the simple way to do this, so the Hubble palette is its own palette for color, okay? So on the telescope, on the Hubble telescope, there's a camera attached to the back of basically the telescope. And it's the same as your CCD camera and your digital camera and your cell phone, but much bigger and much more expensive, and exponentially more expensive because it was the government. And but that camera is actually a monochromatic camera. It doesn't see color, okay? Monochromatic cameras are actually easier to get better data from. It's easier to keep them cool. They resolve more data. You know, they're more sensitive, which is what we're looking for. Like, a real scientist could care less about color, like, because all you need to do is put a filter in front of it, and you know exactly what type of color you are looking for. So when we see things like hydrogen exists, everything that emits color that we can see, those colors are photons of light, individual particles of light, and they have a particular energy to them, you know, and each energy of photons corresponds to a color, whether it be the visible spectrum that we see, the Roy G. Biv, or it may be below red or infrared, or it might be radio waves, or it might be ultraviolet, or it might be gamma rays, which we'll get into a little bit later, you know, which we can't see, but we know what the wavelength of that light is, and we can build filters to isolate only that one type of light. So let's say we're taking a picture of the Orion Nebula here. So Rogelio, I know exactly how he took this shot. So you're gonna actually take your telescope and take long exposure shots, put a filter in the front that only resolves the hydrogen, okay, which is gonna come out red. Hydrogen actually, which we're gonna get into in a minute, a lot of the red that you see in space, a lot of things are red because most of space is hydrogen. About 75% of the entire universe is hydrogen as far as mass, or of matter is concerned. So you're gonna see a lot of red. Then you're gonna put a green filter in, or like or an oxygen filter, or like a sulfur filter. Like, we're gonna resolve specific elements that are out there, and then we're gonna tie that to a particular color. Okay, so when Hubble has all these files and stack them on top of each other, okay, here's my sulfur file, here's my oxygen file, here's my nitrogen file, I know what color that would look like, so I assign that color to that shot. When you're done, you get a super, super high resolution photo. And this is Orion, this one's a lot easier. So anyway, let's get moving on. Does that answer your question?
Yeah.
Pretty good? Okay, good. Let's get moving here. I'm always worried about not going long enough, and it always goes way longer. So traditionally, like nebula, we're kind of categorized a little differently. Nowadays, we do it a little simpler. There are three major categories for nebulae, and that is reflection nebulae, emission nebulae, and dark nebulae. Those are the three main categories that we consider things. All right, and they're when we see them, these cloudy things in the sky, they're caused by different things. So let's just jump right into the first example here, which is supernova remnants. So when a star is big enough, when it ends its life, it actually explodes. It goes boom, and it's the most violent, most exciting, awesome thing in the universe. This is the Crab Nebula. This is a lot of people's favorite shot. This is Messier object number 1. Charles Messier was an astronomer back in the late 16, early 1700s. Messier, I believe, Charles Messier. I can't remember where he's from. Oh, France. So, which is why he did everything wrong. So the Messier database is actually full of all kinds of objects that when you look in the sky, we call this Crab Nebula, but this is the Messier object number 2. M3, M5, M27, M43. There's all these numbers that correspond to a database that he came up with. And basically what that database really is, I don't know if you know this or not, but the Messier database is a database of things not to look at. That's exactly how he described it. He actually built this database of things not to look at because he was looking for comets. So M1, the Crab Nebula, was not a comet, so move on. That was the purpose of that list. Comets were all the rage back then. Edmund Halley just predicted the first one for the first time in human history. Just before that, it was a big to-do. But here's an example of the Crab Nebula. All right, so this is what's left over after a massive star exploded. I do have a little bit of notes here. So this one's pretty far away, but still, most of the really exciting, bright things are actually closer than you would think. Most of the nebulae that we look at that are close enough that we can resolve, get the colors, get the beautiful images from, actually come from a very local region of our galaxy. We live in what's called the Orion Spur of the Sagittarius arm of the Milky Way, and most of these nebulae that I'm going to show you are very close to us. This one's actually on the kind of the outer limit. This is 6,500 light years away. 6,500 light years away. Pluto is like a third of a light year away from us, something like that, 0.3 AU, something like that. It's really, really far away. The fastest thing humans have ever built, it took 10 years to get to Pluto. I mean, it's far away. So this is about 1,600 light years away. So this is when a star exploded, and this star exploded. We know exactly when the star exploded, actually, which was July 3rd, 1054. July 3rd, 1054. Guess how we know that? Because basically every culture in the world actually recorded it one night when they saw it go off early in the morning, and it blew up. And when stars blow up in the sky, even being as far as away they are with this one, they actually gain luminosity. They're so bright, they outshine the combination of all the output of all the stars in the entire galaxy all at once. It becomes the brightest star in the sky, brighter than Venus, and it's about as bright as half of a full moon. And it stays in the sky and is visible during the day for about 2 years. This was about a year. This one was about a year. I got another one later. It was about 2 years long. It's amazing. And stars go off pretty often, about once per 100 years per galaxy. But this is the Crab Nebula. So in the middle of this nebula is what's left over, which is called a pulsar. It's a very rapidly rotating leftover core of a star that is densely packed with neutrons. It's in the family of neutron stars. But the energy that star is actually radiating is what's causing most of the color here, most of this to glow. Okay, this gets me to my first category, which is called an emission nebula. So this is a supernova remnant. Why do we call it an emission nebula? If it's a supernova remnant, let's just call it what it is. But no, it's more specific because an emission nebula actually means that the light from all the clouds, all the debris there, actually comes from it itself. What I mean by that, I'm going to start you hard and we're going to get easy earlier, is that the energy that's being put out by the star in the middle, okay, which is a pulsar. This thing's rotating 30 times a second, the leftover star, in the middle of this, and actually I have a picture to show you afterward. But the energy being radiated from that star, it's super high energy. You're looking for ultraviolet. That's really what you're looking for. We have visible light just above, you've heard of Roy G. Biv, red, orange, yellow. G is green, right? And then blue, indigo, violet, and then what's above violet? What's a good Latin way to say above violet? Ultraviolet, yeah. So high energy light that we can't see that causes cancer and sunburns. What's that?
Tan.
Yeah, I mean, you're a little deader, but you're prettier. It's a trade-off, you know? That's up to you. That's your call. Your mileage may vary. Okay, so the ultraviolet light here is actually, the light is actually coming from the star. It's interacting with the dust here, all of that filament there on the outside. And all the atoms that make up the dust in this, the electrons on the outside of every atom, mostly hydrogen here, the electrons are actually stripped away from this high energy light. And it's actually pretty cool because even in the large clouds of especially hydrogen, when those electrons get stripped off, those electrons can travel for like hundreds of light years before they recombine again with the nuclei of another hydrogen atom, which would just be a single proton. And it will actually emit light when it does that. When that electron gets stripped and it recombines with the proton or nuclei of another atom, it emits light. And with hydrogen especially, mostly what you get is red. Sometimes you get a little bit of blue. So the energy from the star itself interacting with the things around it are actually what's causing that light to happen, all those colors to happen. Emission, it emits light. Okay, just taking in those. Which reminds me, I probably should have started from the very beginning telling you what all that stuff is. I mean, that's kind of important. I've been trying to memorize something, and my friends here know I've been trying to memorize it. All those things in there in nebula are called polycyclic aromatic hydrocarbons. That's what those things are, besides the hydrogen itself, which is basically soot. If you take a match and you light it, and what's left over at the end is soot. What's left over is a lot of actually what's in there. There's a lot of carbon, there's a lot of oxygen from the way the star actually fused things together when it blew up. A lot of that's out there. You're actually going to see the blue in the middle, I believe, is actually oxygen in the middle of this one. The red and the green correspond to hydrogen at different temperatures, I believe. And then orange is sulfur on that one, if you follow the palette there. I did want to show you quickly, though, that quickly rotating star in the middle. And the reason it's rotating fast is that stars actually do spin. They're not all the time they're just sitting in one place. Sometimes they spin fast, sometimes they spin slow during their ordinary life. Our sun spins. But when these stars explode and when the core collapses, because it's already spinning, when that core actually collapses, it spins faster and faster. It's that law of angular momentum I brought up last time. The same way that a figure skater pulls in his or her arms and spins faster. When that star actually shrinks down at the end of its life, it becomes faster. And it can spin incredibly fast. They can spin so fast that this one, I actually have a sound bite. It spins about 30 times a second. You have some that spin hundreds of times per second. They're called millimeter pulsars. And they sound like a musical note more than they do clicks when you look at a radio telescope. But we actually took a picture of the Crab pulsar, and that's a real picture. That is not an artist interpretation. That is a real picture of that bright one in the middle is the pulsar, which is a type of neutron star. So imagine a star that's many times more massive than our sun, but it's about the size of Toronto. Very bright, very magnetic, very energetic. Takes about 4 trillion years to cool off. Anyway, but I want to just show you a couple more versions of the supernova remnant. This is Tycho Brahe. If anybody's heard of Tycho Brahe, who's a crazy man. He actually saw this one go off a few hundred years ago. And when we observe it now, this is actually what it looks like. This is what's left over. So something similar between the Crab Nebula and Tycho Brahe. This is it has another name. It looks like a phone number in astronomy. Not everything has a really cool name. Some of them look like phone numbers. What's up?
So you mentioned earlier that Crab Nebula was a star that had gone supernova, and they had seen it in the sky for a year, probably. So was that the duration that the star was actually being in supernova, or what? Like I'm kind of curious as to like how long a supernova takes to see.
Yeah, I mean, when it blows up, you know, it's radiating all of that light and that energy over a certain amount of time.
But explosion is like happening in fractions of a second, and that's why I'm asking, because it might be so massive or energetic that it's changing years, which is insane.
I mean, that's kind of the answer. Like, stars are so big, especially stars like this, they're so massive. When they blow up, it takes a long time for like that flash to actually happen. You know, and these remnants that are left over, like this is actually getting bigger. It's still blowing up, and it's hundreds of years later. You know, the Crab Nebula, that was 1054. I mean, that's almost 1,000 years, and it's still there, doing its thing. They only last about 10,000 years, to answer your question further. Like, supernova remnant average about 10,000 years in how long they'll stick around. That's why we only see so many of them. There are lifespans to a lot of these things, except for white dwarfs. I mean, those things last forever. I mean, we're talking like 2 to 4 trillion years. The universe is 13.5 billion years old. That's like 15,000 times older. You know, so white dwarfs, they cool off and turn into what's called black dwarfs, which are just giant balls of coal, essentially. And none of them exist because the universe is not old enough. But stars do cool off, especially things like this. But I want to show you another one, which is showing you an example of something that's a little more asymmetrical. Stars do all kinds of different things. They're kind of far away from each other, but they're still interacting with other things. They're not so isolated, even though there is much space. This is a good example. This is what do they call this one? LMC N49. So this N49, so LMC stands for Large Magellanic Cloud. So this actually is not in our galaxy, but this is in our closest neighbor, what do they call it, dwarf galaxy. But this is the remainder of another supernova, just showing that they don't have to be symmetrical and spherical, as always, and this is actually going to get a lot more interesting in a second. But the reasons for this can sometimes be debated, sometimes they're a little more solid, but with the debate of how these things become asymmetrical, it's just because there may be different things happening in the star. It could have interacted with something else at one time as it was coming close to its end. It could be spinning too fast, it could be spinning too slow, it could be part of a binary system, which is two stars interacting with each other. So you don't always get a star that blows up symmetrically into this big ball-like thing. You get these big sporadic leftover wispy things sometimes when you're done. Which brings me to my next example here, which is the Vela Nebula in Vela. This one's 815 light years away. Which is pretty close. Remember, the Milky Way galaxy is about 100,000 light years across. So these distances are quite close. So you'll hear the Veil Nebula, which is a part of this. This is actually about 4 times as big as this one shot. This is a massive object in the sky. This is also a supernova remnant, I believe. And this actually blew up about 1,000 years ago. And nobody in the world actually recorded this one. But there's a reason we know that it went off about 1,000 years ago. And that's because we can actually detect titanium. Titanium-44, which is an isotope of titanium actually decaying in this entire area, which, knowing anything about the titanium, you know that it would have decayed. If this was older than 1,000 years, it would have decayed long ago. The fact that it exists means that it's actually there, which is really cool. So the blue here actually represents the oxygen, and the red represents the hydrogen gas in this one here. So let's hit this one here. This one is the Ring Nebula. So this is actually a different type of nebula. This is called a planetary nebula. So when stars aren't as big as the star that was, say, the Crab Nebula, when a star is smaller than that, and it doesn't have a chance to blow up when it dies, stars kind of fizzle out when they're done. The majority of stars, to be specific, the majority of stars just fizzle out. They do not blow up. Stars like ours, G-type stars, these medium-sized stars, they don't have enough mass to explode. What they actually do is they fizzle out, and the core actually contracts. Reference, like, a few of you have been to my other talks about how stars die, so I'm not going to go into that. You can talk to me later if you want. But when the core collapses, the outside layers of the star actually get thrown out into space. Okay, the outside layers. And those can contain some things, besides just the things that we think of stars being, like hydrogen and helium. It can actually contain things like oxygen, carbon, nitrogen, and even trace amounts of heavier elements from the star's formation. Okay? And this is what you're seeing here is actually the white dot in the middle is actually a white dwarf, which is basically a star about the mass of our sun, but about the size of Earth. And remember, 1 million Earths can fit in the sun. So that's really dense and really, really tiny. Okay? So, and it's what's lighting up the nebula around it. But the nebula is actually basically, think of it this way. Think about the fate of our Earth. Okay? And this is argued among astronomers. So don't take this as gospel or anything. But when our sun starts to die, it will actually start to expand, and it will eat Mercury, completely engulf Venus, and there's a chance that Earth might get swallowed up by the sun when it gets close to the end of its life. I've heard and I've read things that say it probably won't. I'm taking the middle ground and basically saying that yes, it'll probably vaporize everything on the surface, but Earth might probably still survive. But remember, like things like Venus and Mercury, those things get absorbed by the star, by the sun, by our sun. And the things that make up what it is are going to be outside on the outside layers of that sun when it does finally start to shed its outside layers. All those little things that made up the surface of those planets actually get radiated out and then illuminated in some cases, like this one, in the Ring Nebula. I have the color profile here. The blue here in the middle actually represents the helium. And the lighter blue on the outside, see how the dark blue is on the inside? The lighter blue on the outside is actually standing for hydrogen and oxygen. The greener that it gets, it actually stands for oxygen. And the reason they mixed up the colors a little bit more is just to get more definition out of these, to get more contrast. So you can see more data as a scientist, basically. The red actually stands for sulfur and a little bit of nitrogen on the inside, where it's a little more yellow. The ring nebula there. And again, this one is being excited and illuminated by the energy coming from its white dwarf star. This is another example of an emission nebula. This is the Helix Nebula. I went too crazy on these planetary, so I'm going to go brief now. 650 light years away. We haven't been able to resolve the white dwarf in this one. It's not the star in the middle. That's never been resolved. But this is another example of a planetary nebula, or what's left over after a star dies. Note it's still kind of circular though, which is going to be interesting because remember, we're looking from one perspective here on Earth. Okay, if you only stand in the corner of one room, you're only going to have one perspective of something kind of forever until you move. And we go around the sun, but really we don't move that much. So when we look at this, when we do see it in the night sky, it pretty much always stays the same. But imagine if we were in a different place. It would actually look a little bit different. And let me jump to that. I'm going to hit the Helix Nebula. This one's actually painted on the wall in the other bathroom, if you're interested. But I just wanted to show that there is some asymmetries here, something that's a little more exciting. Before we get there, I want to show this one. This one's one of my favorites. This is called the Eskimo Nebula. This one's really cool. The Eskimo Nebula, this one's pretty far away. This went off about 10,000 years ago. But most people ask, like, it doesn't really look like an Eskimo. But if you've ever gone out with a telescope and looked at it, it actually looks like an Eskimo. I've seen this. So I have this shot here. It looks a little more like an Eskimo when it's small, because it's actually smaller than that when you look at it through an eyepiece. Unless it's a really big telescope, but that's what you're going to see. It looks kind of like an Eskimo. Another one of my favorites. This is the engraved hourglass nebula. This is one of my favorites. It looks like an eye in the middle. That's another planetary nebula. When a star dies, it becomes a white dwarf and radiates everything outward. Sometimes you're actually going to see phenomenon like this where it's not completely spherical or circular, but it kind of is spherical, but it's the same on both sides. Where does that come from? And the answer can come from different places. The most common answer is it's from binary star systems, which is when two stars actually form next to each other. The majority of stars in the sky are not single stars. They're actually binary stars. Anybody seen Star Wars? Yeah? It's a terrible movie. You should watch all of it. Yeah, remember on A New Hope, when he's watching the sunset, there's the two suns setting? That's probably more common than you would think. Like, most star systems are binary or trinary systems. This is a good example here, the Ant Nebula. I don't know why they call it the Ant Nebula. Oh, that's a good reason. Dang. See, we need to pay you to get super high every day and name nebula.
I mean, I think it sounds like a great job.
Yeah, we're gonna pay you $11 an hour. Oh wait, no, it's 2020. What is it, $13.50? All right, cool. But this is another example of one of those binary star explosions. And one more example here in the Butterfly Nebula. What's really cool is actually the bar in the middle here. If you see all the dust there, the bar in the middle is actually super, super heavy dust. Some people are thinking that it was already on its way, this little dust glob. It was already on its way, and it actually collided and interacted with the middle of this planetary nebula at the end. That bit of heavy dust wasn't there to begin with. That's actually really, really cool. Okay, so we talked about emission nebula, the gas, the hydrogen, the polycyclic aromatic hydrocarbons, or soot, that's in these areas. They absorb the high energy ultraviolet light from stars. The electrons get stripped off. When they recombine with other atoms, they emit light, and that's where those colors come from. Let's get into another thing, which is actually called a reflection nebula. Not emission, but a reflection nebula. This is a cool shot taken again from my buddy Rogelio. This is the California Nebula on the left. I don't know who called it that. Yeah, it kind of looks like California. And it's all alone, which is where it should be. Okay, and on the right is another constellation that is called the Pleiades. Anybody here heard of the Pleiades? One of our favorites. It's fantastic. Also known as Subaru in Japanese, which has 6 stars and not 7, by the way, which is why your Subaru car has 6 stars on its plaque. And they're in the wrong place. But every other culture had 7 stars. A couple had 9, actually. So on the right is the Pleiades constellation. Now, when you look up at night at the sky and you see the Pleiades, it looks like this really faint little, like, conglomerate of little tiny stars. It's fine. It's quite faint. But if you actually held a telescope up to it, I'm going to shoot you here. This is a close-up of the Pleiades. Now, you see all the cloudiness around the stars there? All the main stars? All that nebulosity? All that nebulosity there? It is not being excited to the point where it radiates its own light. It is not emitting its own light. It's actually reflecting the light of the stars in the Pleiades. It's reflecting the light, which actually makes it look a little bit blue. This is a real thing. And you can actually do this experiment, because the gas here is actually, it's not gas, it's actually dust. It's a lot of that soot dust, okay? So I've actually read a lot of papers on this, and I don't have the answer on this, but there are 2 competing ideas to the gas in the Pleiades. One idea is that the Pleiades has actually burned off the dust, sorry, not gas, but dust. The dust in its area. When these stars formed, these stars are actually blowing away all of the dust over time, and this is what's left over. But I've also actually read a couple papers recently that say that the Pleiades are actually moving. All the stars, the major stars in the Pleiades, are actually moving in the same direction at the same rate, which is they're actually running away from Orion faster than he's moving towards them, because the 7 sisters were afraid of being raped by Orion, if you know the Greek mythology. And they're winning the race, to be fair. You know, and what's really cool, it's really, really cool, if you're super, super nerd on this, if you go and you look at a star map and you press play for what the stars are going to do for the next 50,000 years, the Pleiades will move away from Orion faster than one star. I don't know the name of the star, but there's one star that's actually pulling back, and he's actually drawing his bow to shoot at them. And all the other stars in Orion and the Pleiades actually stay together, but they move into the sky. The only star that moves in any way that's like, in any way that you would care, is the one star that would represent his hand drawing back his bow to shoot at them because they're running away and he can't catch them. I think it's one of the coolest things in astronomy. Okay, by the way, side thing. So, but the dust is actually illuminated around here just from the light from the stars themselves. This is called a reflection nebula. It reflects the light coming at them. And again, this is soot. This is what's left over when you burn stuff. Here's a really cool thing. Why is it blue? You can actually do an experiment at home. Who here smokes cigarettes? Nobody. Okay, so nobody can do this experiment. Okay, so everybody start smoking. This is 1971. Yeah, right? So the size of every particle of soot from a cigarette is almost identical to the size of every particle of soot that you get in the universe. Astronomers actually use it's like the cigarette analogy here. If you went into a dark room and had one single white light, and you took a drag on a cigarette, and you blew it into the white light, it would be blue. The blue is not the color of, it's not like interacting in a way that the blue comes from the color of every particle itself. It's the size of the particles, the way they scatter the light, that scatters the red away, and then what you end up with is blue. What we see is blue. It's not intrinsic to it itself. It has to do with the size and how close they are to each other. That's why we get the blue colors here. Okay? So that is a reflection nebula. It means that reflection nebula is reflecting light from their stars. It is not emitting their own light. It's not because they're excited. It's just like shining a flashlight on something and says, it's over there. That is a reflection nebula. And I'll show you another example of a reflection nebula here in a minute. But the last category is called a dark nebula. Okay? A dark nebula is mostly, it's the same thing. It's hydrogen and soot, basically. Look at this Carina Nebula again. So we see all the colors, all the wispiness, and I see all the dark regions, all these pillars kind of sticking out here. I wonder if I have my mouse here. Can I do that? Okay, sweet. Okay, right here, we're going to zoom in on this here in a minute. But this is the wide field shot of the Carina Nebula. This is called Mystic Mountain. We're going to look at some cool things going on in here. But like, look at all these dark regions here, okay? They're not emitting light. Like, you imagine that all this light color here would continue on if it weren't obscured by this giant pillar just getting in the way, okay? So, and that's exactly what's happening. These dark nebula, which is what those darker things are, they are super densely packed regions of this space of dust. Super, super densely packed regions. Which is not saying much, to be honest. When you look at these massive clouds of hydrogen gas, like these giant nebula here, like look at someplace like up here, okay? Where am I here? Like up in here, where it's kind of opaque, but you can still see through to the stars behind it, okay? Now think about how much stuff is there? What makes up this gas cloud? Now, we actually have numbers for these. In these gas clouds, we're looking at a concentration of about between 100 and 1,000 atoms per cubic centimeter. Between 100 and 1,000 actual particles per cubic centimeter. So about the size of a sugar cube, okay? In these super dense regions, we're talking about 1 trillion particles per cubic centimeter. That's a big difference. But what's really funny, in the air that's between you and me right now, this crystal clear air, there is, I think, like 50 times that in particles per cubic centimeter in our atmosphere here. So this is very, very, not much is going on here, but when you have a lot of it spread over a huge distance, you know, it gets dark really, really fast. It gets colorful really, 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 really fast. So but these dark nebulae here, those are super, super densely packed areas of dust and gas. Now, who here remembers what stars are mostly made out of? Hydrogen, that's correct. Okay, with a lot of helium. So 75% of the universe is hydrogen. 75% of our sun is hydrogen. 75% of a nebula is hydrogen. Hydrogen kind of just sticks around as element number 1 on our periodic table. The simplest of all the elements. It is 1 proton and 1 electron. Now in these dense regions down here, that means that a lot of them are clumped together at the same time. Now what do you get from that? Is these are what we call star-forming regions. Okay, so dark nebula specifically are where you get a lot of star formation. You have a dense cloud of the things that make stars, and when gravity starts to take over and everything wants to collide with each other and interact with each other, you get the birth of stars. When I called this the clouds of creation, I meant it. All of that there has the potential to make new stars every day. Now, look at this right here. This is always one of the funnier things about the Carina Nebula to me, is this is always the highlight. This is Mystic Mountain, and it is upside down because this is the common shot you will see of Mystic Mountain. This is 7,500 light years from Earth. These pillars here, this one is about 3 light years tall. Okay, 3 light years tall. Now, inside each and every one of these clouds, or inside all of these clouds, new stars are being born, and we can actually see them being born, which is actually really cool too. I'll show you in a later slide how we see that. But when they're actually born, we can actually see their infrared light being radiated out. But there's actually evidence of stars being born in other places, like this up here. You see that? Okay. So, Years ago, somebody actually put something out there that said this was a star that went supernova in this gas cloud. And he was clearly wrong. Yes.
Sorry, you lost
Yeah.
me. You lost me on the last slide.
Sure. Oh, sorry. Okay.
Okay, so,
Start from the beginning. Okay.
No.
Welcome, Yaya Brewing Company.
on the slide,
They got great beer. Yeah.
you said that there was a bunch of helium available.
Sure.
And the
Hydrogen.
And then for hydrogen
Yeah.
available. I meant hydrogen.
Yeah, I know.
Why would it just gather in stars?
Why would it just gather into stars? Because gravity.
Why
You always ask the best questions. It's like I avoid going down these super.
Make that into stars.
Okay. So there's. Everybody ready for this? You go on a journey? So there's.
Last time you encouraged questions. Are you still encouraged? Because I just asked questions.
As long as it's you.
Okay,
You've been to every single one of
You can
these.
excuse it, and I'll just wait till after.
No, it's fine. No, I encourage questions. Big time. So if I had to pee a little bit more than I have to right now, I'd say I don't know and just bail.
How about later? Answer me later.
Okay.
Get back to you later.
No, I mean,
You are dancing.
huh?
You're dancing a little.
I'm dancing a little bit. I kind of gotta pee. That's fine. We're gonna do this, but it has to do with thermal equilibrium and what's the other one is hydrostatic equilibrium. Okay, it's when these stars actually, when these gas clouds actually form. Some regions are actually more dense than others, and the denser regions, basically because of gravity, every particle. This is Isaac Newton. Every particle of matter is attracted to every other particle of matter. And the attractive force is inversely proportional to the square of their distance. We're not going to go there. But everything is attracted to everything else through gravity. Now, in these clouds, when they collapse into these big nebula clouds, certain areas will be a little more dense. And then within that little denser region, you'll actually have a super dense region within that region, and then a dense region within that region. And when you have a cold area of this gas, the dark nebula are very cold. That's what it actually takes to actually make a star basically start happening. And the density and the size of the cloud will dictate how big the star is going to be when it actually starts to fuse things together. Okay, because there's this inward pressure of gravity, but there's also, the more pressure you put on something, the more heat you actually generate. But there's actually a point where that becomes irrelevant. In physics, where you'll actually put so much pressure on something where it doesn't, it'll actually not get hotter anymore. And there's a complicated process that leads to the formation of actual stars, and then those hit their equilibrium in its own way, which is basically a tug of war battle between exploding out and gravity pulling it in. Okay. Nebula act the same way, but they're a lot less violent. They're a lot less nuclear than a star itself. But because nebula make the stars operate by the same mechanism. We just see a little different phenomena happening. Does that answer your question?
Yes.
Mostly? Okay.
Thank you.
Okay, cool. So I just wanted to say what this was the first thing I read when I learned about Mystic Mountain years and years ago was this was actually left over from a supernova exploding on the tip of the spire here, and that is actually very not true. This is actually a star that formed on the tip here, and as it came together and as it collapsed, it spun faster. No, Google. Oh man, you are a bitch. Okay. Google. Still better than Siri. Okay, but this is actually a star that formed, and as it formed, it was spinning. As it collapsed down, it was spinning. And as it was spinning, it actually sent this ejecta here out. It sent it away from this pillar here. As it's spinning this out much in the same way that if you took a ball of pizza dough and spun it, it became flat. That's actually what's happening way up here. There's a star being born inside that cloud. It is absolutely fantastic. We're going to roll through here really quick. This is the Eagle Nebula here. These are the pillars of creation, made famous back in the 90s by Hubble. Side fact again, too, by the way, Hubble, I got a big thing for Hubble. We're going to do a whole thing on Hubble here one day. But, so we sent Hubble up, we built it, launched it, put it in space, turned it on. Somebody put a washer on backwards, and the first shot was out of focus. It was insane. And the guy that went up there to fix it is like an American hero. He was running out of oxygen. They're like, you got 2 minutes of oxygen, it takes you 5 minutes to get back. He's like, I'm gonna fix this thing, and he fixed it. And he got back through the airlock, back to the space shuttle, like with like 10 seconds of oxygen left. Total American story. It was great. He needed to fix this. But that being said, the first shot that was taken from Hubble, the first picture taken from Hubble when it was sent up there, more was learned from that one photo than anything has ever been learned by one scientific instrument in human history. It's been said by more than one person. More was learned by the first instance of using it than any other scientific instrument has been able to deliver us. It is the greatest thing we've ever done and has given us the most insight into our cosmos. When they did that, they did the Pillars of Creation there. That is 1995 there on the top. Here's a zoom in of it. You might recognize it, the Eagle Nebula, the Pillars of Creation. We actually imaged this back in 95 and we did it again in 2017. I didn't get that picture here, but everything is actually different now. We can actually see this evolving over time. All of this is actually a little bit different. I think this is a little more opaque now. And like this has moved over to the right, and some little spires when you zoom in super far here are a little bit different. But this again is another big star forming region. They call it the Pillars of Creation because they are literally pillars of gas that are creating stars and the things that create things that are needed for life itself. What's really cool is this is all being illuminated by stars up here and up here, which are basically the stars that are in direct line of these spires here. That's where the light is actually coming from. And here's a way zoomed in shot of that. It's amazing that we can zoom in this far. Again, when I said that Carina Nebula shot where you can blow it up to it's 16 feet long, the resolution on these photos are unreal. And I'm allowed to show them to you because every single one of you own that picture. That was done with your tax dollars. This is Hubble. I don't need any fair use stuff. Just saying. And the other one should take it by my friend, so he can punch me in the face, it's fine. Okay, which brings us to our last category here, which is dark nebulae. Okay? I was already talking about dark, but here's another example of actually dark nebulae here. I'm sorry, I was already talking about it. This is just a cloud of dust that is just so dense you can't really see through it. Just like the Eagle Nebula, we'll talk about the Horsehead here in a minute. But what's really cool is as the light from the stars behind this is not a hole in space. There's stars everywhere there. It's just a big cloud of dust there that is so thick that the light actually scatters as it's passing through it so much that we just don't see it. But what you do see is as it does that, you get this, you can still see some of the heat and some of the red from some of the stars. So in the less dense areas of this, right around the edge, you'll see a lot of red. Just like if you drive through a sandstorm, at night or something. I wanted to bring you back to Orion here, being one of our favorites, because I have a kind of a cool treat at the very end. Looking at Orion here, what's cool about Orion is it has examples of pretty much everything. You have this emission nebula here, Barnard's Loop. You also have the emission and reflection nebula here in the Orion Nebula. You have dark nebula, which is down here at the Horsehead, which we're going to zoom in. And you have another reflection nebula here, which is the Witch Head Nebula. The Witch Head Nebula is actually illuminated by Rigel here. Down here, this is Betelgeuse. It's a big red star in the sky. You can actually see it. It's red outside. Its other star is Rigel. This star, Rigel here, which is the brightest star in Orion, by the way, but it is called the second brightest, which pisses me off. It is Betelgeuse is alpha and Rigel is beta. This is zooming into the belt here. So this is Orion's belt. We're moving in quite a bit. This is the Horsehead Nebula. You can kind of start to see the Horsehead a little bit more here. This is the iconic Orion Nebula, or the sword of Orion here. When you look up, you'll see these three stars. But this is considered the sword. If you're in a really dark place in the world at night, you can actually see some of the nebulosity with your naked eye. You don't need a telescope or binoculars. You can see some of this with your naked eye. But I want to zoom in over here to the Horsehead Nebula. And the shot I actually have is an infrared shot taken by Hubble. So this would normally be dark, just completely dark, but because we took this picture in infrared, which is basically we're able to see heat, we can actually see all the stars on the other side and within it. These are just stars being born inside the Horsehead Nebula every day here. Move on to here. So looking again at the Orion Nebula, when I said clouds of creation, okay? So the Orion Nebula here, what is the exact size? I think it's like 1,000 light years across. I had to write it down. Orion. Okay, so the nebula itself here, from here to here, is about 20 light years across, okay? Inside that is about 2,000 stars. But everything in here is actually illuminated by 4 main stars called the trapezium. We've actually seen 700 stars formed in the Orion Nebula. We've actually seen it. And looking at it, it looks kind of circular here. You know, it's kind of cool. What's actually really cool about the Orion Nebula is we look at the side here, and I was talking earlier about perspective. It actually goes.
So the physical reactions between what a atom and outward and a compound are completely different.
So we don't know. Okay, so there's your answer. No clue. Which is the best answer in all of science. It is the best answer is I don't know. Awesome. Well, big thank you to Yaya for hooking it up with us. You guys all got raffle tickets, so we're gonna give you something. All right, look at your tickets. We're gonna give some stuff away.